All right, so I am doing this little lightning talk on a bit of work I did earlier this year about making our backend and Node a bit faster. So the motivation for this was that on our most recent chips, the Ice Lake series, they deleted the FP64 hardware. And because OpenGL is awesome and makes FP64 a required feature for OpenGL 4.0, we had to emulate it. And so there was some work that was done under one of the summer code type projects to do an FP64 implementation in software, but we never actually wired that up. So Matt did a bunch of work to wire it up in our driver, and what we quickly discovered is that when you have a shader with tens of thousands of instructions and tens of thousands of basic blocks, the compiler takes a long time. Prior to me starting on this project, a piglit runtime was about 7 hours, with the debug flag set to force software FP64. So I did 4 major things. I'm just going to kind of blitz through each one of them and talk about them. So the first thing I did was to improve the copy propagation pass performance in the backend. So our backend copy propagation, notice copy propagation is fairly nice. It uses a hashing structure that lets us do it in linear time. Our backend compiler copy propagation worked by you look at an instruction and then you walk all the instructions back up the program to see if you can find the instruction from the propagation. We had some sort of hash sets that we were using that weren't very great. But I found one particular bit of code where I was able to drop something from n² to linear time. And let's see here, I scroll down and I have some piglit, I have some runtime numbers. It's at the bottom. So before doing this, it took about 4 minutes, 36 seconds with no validate disabled. So the 7 hours is with no validate enabled. And after doing this, it took 2 hours, 48 minutes. So progress. All right, next thing I did, another merge request, was I did some perf traces with full debug builds and found out that no validate was taking forever. Doing a bit more digging, I discovered that the problem was that no validate was validating all of our use def sets for SSA values by using a hash table of structures containing hash sets. It turns out that this is not particularly performant. So I replaced this with a single hash set that gets, based on the number of SSA values we have, sort of pre-resized so we don't end up with any growing. And that, let's see here, scroll down to the bottom, I've got numbers. Maybe not at the bottom. Oh, come on, I know I have numbers for this one somewhere. Maybe it was at the top. Right, so I timed this one using ShaderDB on my laptop. And if I run a debug build with no validate equals 0, it took about 5 minutes, yeah. I'm failing to divide. 20 minutes. Anyway, 3,000 seconds. With validation enabled, it took 20,000 seconds, and with validation enabled and this change, it took 6,000 seconds. So it took no validate from massive overhead to about double, which is way, way better. So the other 2 things I did are actually in one MO. And this MO does 2 things. One is I made some changes to the core register allocator in util to use some bit sets rather than individual booleans in various places to allow us to vectorize some of the code by walking the bit sets 1 word at a time instead of walking it 1 element at a time. And this massively improved the performance of the core register allocator in the case where you start spilling because it wasn't doing quite as much dummy iteration. Made it about 2 times faster, 3 times faster, something like that. And then the bigger thing that I did in this MR was I refactored all of our register allocation code in our backend compiler to not reconstruct the entire liveness interference graph every single time you spill a single register. So our previous thing was we would try to allocate, we would spill a register. insert some spill code, recalculate the entire interference graph, reset up the register allocator, allocate again, fail, spill, repeat. And so instead, what it now does is it builds the interference graph once, and when it spills, it carefully modifies the interference graph to just add the new things properly so that we can avoid this spill loop. So the result of these two things together, there were some minor ShaderDB changes, and I have some numbers here. So before numbers, I lifted after the after numbers for some reason. So before numbers was my 2 minutes 48 number. Yeah, 2 hours 48 minutes, and afterwards was 1 hour 40 minutes. And then I think this one also contains sort of the sum total. So these are the numbers on these are kind of scattered because of the order in which I did them versus the order in which they landed. But when you put everything together, it starts off at, oh, this is with another set of flags. These all have different flags, which makes it harder to see. Oh, wait, this is running a limited subset. So 2 hours down to 14 minutes is kind of the overall final thing. Yes, the hours are bouncing around all over the place. I might have after and before backwards. Now I am very confused. I believe I have after and before backwards. Huh? No, I have after and before backwards. So it went from 14 hours to 2 hours. There we go. No, it definitely did. Some of the RA changes, I also have some numbers on what it did to ShaderDB. It shaved off about 10% of the runtime for a ShaderDB run with an optimized build, so that means it actually does matter in real life. And it made the Vulkan CTS runtime in CI like 40% faster because it's totally compiler bound. Anyway, that's what I did. Pretty short, sweet, to the point. I'll let the next person go.
All right, hello. I have a short presentation of a work-in-progress solution for XWayland multi-DPI, which is kind of still a problem. And shortly about the problem, the common scaling approach on XWayland is problematic because either the XDG output size is ignored, and by that then it's not multi-DPI. So this is the approach which is currently taken by Gnome, to my knowledge, or the upscaling is blurry with each XDG output, and this is what Quinn in a Wayland session does, and also Weston and double roots. Correct me if I'm wrong, but that's what I know. And yeah, the problem is that X11 is not designed for multi-DPI in the first place. And toolkits often support only a single scale factor, if at all. Like in Qt, it's Qt scale factor, although there's also an environment variable for multi-DPI, but at least in GTK, I think there's only one environment variable for scaling all the outputs together. So that's a problem, and my solution proposal. Okay. Yeah. I have it on X11 because I thought then it would work well, but not really. So yeah, okay. Now you can see it's on GitLab for X server. It's a merge request already open for a few months, but now there's some progress again, and yeah, so that's the solution proposal. I call it max factor rescaling, and the idea is to take the maximal scale factor of all the Wayland outputs, and then scale the XWayland outputs with the quotient of the max factor of all the outputs and the respective output factor. And the outcome would be that high DPI aware clients are scaled when with this max factor and input coordinates are translated back and forth between XWayland and the X window manager part of the Wayland compositor, and they are downscaled again when the buffers in the compositor. So it would look something like that. As an example, if you have 3 screens, 3 displays with different resolutions and different scale factors, so you can see in the lower diagram what the view would be for the logical compositor space. So with the scale factors, they shrink basically, and then you have them laid out like this. And continued in XWayland, you would then upscale these, or at least tell XWayland that it should view them as like this. And for example, an input coordinate then gets translated just by multiplication with this one common max factor rescaling factor. And so with a linear transformation, and it's quite easy to reverse. Yeah. Like it says, simple linear transformation for the advantages. High DPI where clients can then render nicely with the right size content, and it's sharp, so nothing blurry. And it only needs minimal changes to XWayland. It's backwards compatible, and one positive side effect is that games do not hide the native resolution anymore if you use XDG output at the moment. This means it doesn't show the native resolution of the display if it is scaled. Disadvantages, there are also some disadvantages. So non-high DPI clients on X who can't provide who are not scaled, like Qt applications, for example, with environment variable, they are then also small, even on low resolution displays because of the downscaling afterwards in the compositor. And the XWM part of the Wayland compositor needs to translate all the coordinates, so there's some work to put into the Wayland compositors which want to support that. And games show too large resolutions, but yeah, that's not such a big problem. Increased resource usage because you upscale everything and it's getting painted then at a higher resolution. And there's this maximum possible screen size in the X server, which I'm not quite sure if it's really 16K times 16K, but I heard 32K. All right, then it's a little bit better, but still at some point you hit this mark, so I'm not sure what to do about that, but that's in general a problem. It just gets accelerated if you upscale. Yeah, there are some alternative approaches which were discussed in the past. For example, creating multiple screens. I know there's some work in progress branch, but I think it got stalled and it sounded kind of complicated to do, but maybe that's still a viable alternative. And the other alternative is to ignore the XDG output size, just like Gnome does it at the moment, and use the X11 multi-DPI toolkit scaling, which, for example, Qt 5.14 has improved upon. But what about GTK? And it complicates the relation between the X11 screen and the compositor space, which then are not linear transformed in any way. So there's not an easy mapping between them anymore. All right, thank you for listening.
Hi, my name is Kevin Bracey, and I will be doing a lightning talk on my OpenChrome project. So currently, the OpenChrome project, I have to actually kind of release this DDX pretty soon because the OpenChrome DRM actually now relies on this. The problem is I've kind of been a little bit lazy on the DDX side, and I haven't actually released a new one for like almost 2 years now, which is kind of pretty bad. And the hang up is basically that there's a connector detection I'm trying to do. I'm trying to make things like more like automatic detection, move towards that. And I kind of messed it up, and the connector detection, this thing here, it works with this one, but it doesn't work with all the models. And I have to probably revert the code back to the old one. Another one is there's like another odd model that that doesn't detect the EDID from the monitor. It's just like one particular model that has like a DVI transmitter, and it's connected. The I2C bus is connected to some little bit unusual configuration. It's not a hardware-based I2C; it's a GPIO-based. And so those are the two hangups of the version 0.7 release. I probably should just do something about it and release it maybe by the end of the year. The improvements for the 0.7 version OpenChrome DDX is that I went through the code, the script that the developers used, and unfortunately they kept neglected it for about 10 years, and I had to go through some of the improvements made in the DDX build scripts that was made around 2010, some of them from Videotron, and I had to grab those and put it in, and in the past it would have build the device DDX, even if it has some unresolved functions, and that was causing a lot of problems. You get some of these crashes when it doesn't resolve all the functions correctly, and it was still building it, which is not a good thing. Now it does not do that. It will reject it. It will stop the compilation. And I also need the new version to support Xserver 1.20. There was somebody who noticed this, and fortunately I haven't released it. And then there were some other virtual terminal after the standby resume has been an issue. In the past code, you will not be able to use it the second time. Basically, I was not preserving the registers when it starts up the code, and now I grab it and I just throw it back in when it comes out of the VT. So now it works. And then most of my development time is really spent on the DRM side, and the DRM side. This is the kind of the timeline, and I don't have any prior experience doing this, and nobody mentored me. I've been on my own pretty much, so the pace is pretty slow, I have to admit. This is a timeline up to until August, and some weird bugs or something hard to find. The last one here is the one in August 2019 I fixed, which is a non-boot bug with certain models. And it worked on this computer, but not on some other ones, and that was a big problem. And also, it was doing some occasional corruption of the cursor. Most of the time, it's okay, but it was not, it was not working correctly sometimes. And I did fix that. So yeah, it was just a one-liner. I was not doing the TTM initialization correctly. Okay. And the progress since August 2019 is that I started working on implementing, moving towards atomic mode setting, which is a hard requirement by the DRM maintainers. So I started doing, first I did a primary plane in, I think it was in March or June 2019, and then I started working on the cursor. Cursor stuff is a little bit harder because you have to deal with the handle. They don't give you the handle anymore when you do cursor plane. So I had to read the code, the DRM maintainers code, and how they're actually now, how they store the image of the cursor and how you actually transfer it to your frame buffer where you put your cursor. These are the issues that are preventing mainlining, and it's really the atomic mode setting. I have the code working, but it's not working currently. I hope I can get it working soon. And the plan is to eventually add acceleration and these other kind of housekeeping chores. And conclusion is that I have to release a 0.7 soon, and I need to add atomic mode setting. So that's it. Thank you.
So, hello everyone. My talk is about our project X.Org desktop that brings VR support to Gnome and KDE. I will start with a very short recap about what currently you have on your standard desktop as input and output devices. You have your monitor, which is a rectangle basically, and it doesn't have really a specific position. Like you have your coordinate system from 00 to 1920 times 1080, and your operating system doesn't really care about where it is. On the input side, you have your keyboard, basically 100 or so keys, digital keys. You can press them and they are pressed or not. And the mouse is similar. It has 2, 3 keys and a relative position. And on your normal desktop machine, unless you are a hardcore TTY user, libinput and X11 or Wayland will handle these devices. So you connect them, and you can automatically control your mouse cursor with it, and your UI will be displayed on your monitor. So what is different with VR stuff? So there you have tracked input. For example, you have the controller on the bottom right, which is the Valve index controller. This is actually tracked in 3D space, so wherever you have your hand, your VR application knows where the controller is. This also applies to the headset itself, so you put it on your hand and you look left and right, and because it is tracked in the room, it can render exactly the application from the direction you are looking in. So with the headset, you have perspective rendering. Even more, you have one perspective per eye. Left and right is slightly shifted, so you get a 3D effect. And a headset has lenses, so your image that you see is actually distorted. And when you render, you actually have to compensate for this. Because of all of this, you don't render to it like a normal monitor. You render through it through direct mode, which is implemented with a Vulkan extension. And what you render, sorry, never mind. Yeah, whatever. Let's not dwell on it. So on the bottom right, this is what you have to render so it looks right on your HMD, which is the VR headset. So currently, if you connect a VR headset to your PC, KDE and Gnome doesn't do anything with it because there is no standard service like libinput for it. So currently, you need a runtime that does that takes the job of libinput and X11, what that does for your traditional input. There are currently many proprietary APIs to access stuff like that, but Kronos made an open API, and Collabora was a part of that. If you want to know more about VR and XR on an open source stack, you can come to the talk tomorrow at 9 a.m. So how do we implement this in KDE and in GNOME Shell? Basically, we have this stack that you see here. On the bottom, there are a bunch of libraries. GXR is a library that implements the connection to a VR runtime that I mentioned. Currently, we only really support OpenVR, which is Valve's runtime. OpenXR support, the open standards support, is currently being implemented. On the bottom, we have Vulkan, which is basically a G-object-based wrapper for Vulkan. That's a nice name. So on top of that, we have XRTestTop, which is our main library. It contains stuff like a container for a 3D window, which is a window that has a position, a rotation in 3D space. And on the top, we have the integration into Kwin and GNOME Shell. With this integration, we mirror windows that you have on your desktop, so you also see them in your VR headset. So some short example interactions that we have implemented is you see a window that is in 3D space. You see your VR controller. There is a ray coming out from the VR controller, and with the intersection from this ray and the window, you have a point where you can click and do a left click, for example, or a right click, or you can just grab the window and place it wherever you want in 3D space. So basically, you have your complete spherical infinite space around you instead of just a monitor in front of you. there's just another example interaction that we have. You can, at the bottom, slightly see buttons that we have for window manager control. And this is just an example where we have layouting in 3D space. So the windows, which are in this case only an image, can be arranged in a sphere around you. This is maybe something like an expose effect where you can choose some window to magnify or minify. We implemented a lot more, but this talk has to be short, so this were just 2 examples. So to close, we have a slide about how you can get involved. We have a IRC channel on Freenode XDC, or we have a Discord channel that you can find on our website if you Google it or DuckDuckGo it. We have all of our libraries on GitLab on freedesktop.org. And tomorrow I will be running demos so you can actually try it out with a VR headset. And lastly, there is an advertisement for a conference that we will be making in Amsterdam. This is next to the Blender conference. There will be topics about open source VR and augmented reality and all of that stuff. So that's basically all from me for today.